Welcome, everyone. I'm Santosh Raikar, a maintenologist. Today, we're diving into plant utilities. We often think of steam, air, and water as the backdrop of production, but in reality, they represent an invisible reliability system that is likely eating your profit through hidden inefficiencies. Let's explore how to turn these utilities from a cost center into a reliability asset. To start, imagine a typical weekend at an integrated mill. Production has dropped to 20%, yet the compressors are still screaming. The utility plant is reliably delivering waste, venting steam and running pumps against closed valves, while the energy bill hides the defects. We need to ask, are these losses a problem of supply, distribution, or simply poor operating control? Why does this matter? Because utilities are production assets. Pressure, temperature, and availability shouldn't just be hidden in a bill, they should be managed. We need to view demand as controllable, distribution as an asset that requires ownership, and quality as the primary driver of equipment reliability. If you can't measure it at the area level, you can't act on it. Our goal for today is to move beyond theory. By the end of this session, you should be able to map your utility demand, quantify baseload losses, select maintenance tasks based on failure modes, and ultimately build a 90-day pilot program to reclaim these losses in your own facility. The first step in any transformation is to see the risk clearly. We need to identify the specific system conditions that transform ordinary daily work into significant enterprise risks. Before we solve problems, we must speak the same language. For instance, baseload is the demand present when you aren't even producing. It's a massive indicator of waste. Understanding your system curve and the true cost, which includes maintenance and production consequences, is vital for a shared strategy between departments. Remember, the loss is always larger than the maintenance invoice. Reliability decisions impact safety, capacity, and reputation. When utilities are unstable, asset life is shortened by water hammer or cavitation, and hidden demand makes your boilers and compressors look undersized when they actually have plenty of capacity. Failure doesn't happen in a vacuum. It develops through a chain. It starts with unknown demand, leads to compensating by raising set points, which overloads the supply and eventually results in poor quality reaching the user. The expensive symptom appears at the powerhouse, but the cause is often hundreds of meters downstream. Warning signs are everywhere if you know where to look. We often accept leaks as background noise, or we see pumps running with no production demand. These aren't just energy issues. They're indicators of a system that has drifted away from its intended design. I want you to challenge yourself with these 8 questions. Can you map your system from source to consumer? Are your set points based on actual needs, or just a guess? Answer these with hard evidence, not just good intentions. This is the gap between a managed system and a lucky one. Once the risk is visible, the next step is to build a disciplined operating model. This model ensures that decisions are based on explicit controls and evidence rather than convenience. Our operating model rests on 5 principles. Most importantly, fix the loss before you add capacity. Don't buy a new compressor if you haven't fixed the leaks. We must also remember that quality equals reliability. If the air is wet at the machine will fail. We call this the Flow 6 model. It's a 6-step journey from mapping your sources to verifying that your savings actually persist. By following this sequence, we treat utility loss as both an energy defect and an asset performance defect. Phase 1 is to map. We need a one-line map that identifies every critical consumer and highlights where our meters are and where our blind spots are. The utilities engineer must be accountable for this blueprint. Phase 2 is to baseline. We have to trend utility load against production. Capturing that no-load baseline is essential because it reveals the true extent of leaks and inappropriate uses that happen even when the plant is idle. In Phase 3, we diagnose. This is where a cross-functional team builds a pressure or temperature profile across the plant. We rank defects not just by energy cost, but by the risk they pose to production stability. Phase 4 is restore. This is the maintenance part, fixing leaks, repairing steam traps, and tuning controls. The goal here is to bring the system back to its as-designed condition before we try to optimize it. Now we move to Phase 5, optimize. With a healthy system, we can safely reduce set points and sequence our equipment for maximum efficiency. This is where we standardize shutdown states so we aren't wasting energy during gaps in production. The final phase is verify. We must remeasure to ensure the benefits are real and that quality at the critical users is maintained. This ensures the savings don't just disappear after the project team moves on. To keep the model working, we need decision rules. For example, if remote pressure is low, the rule is to measure distribution loss before raising the source set point. This prevents short-term convenience fixes from becoming permanent, expensive policies. A model is just a drawing until it becomes executable. We need to translate these steps into a field workflow with clear ownership and a regular management cadence. Reliability often fails in the gaps between departments. While the utilities owner owns the overall strategy, operations must control demand, and maintenance must restore defects. Everyone has a role, but accountability must be singular. Standard work turns intent into repeatable execution. By moving through the flow 6 steps and adding a sustained phase for auditing, we create a loop that constantly learns and updates the operating standard. Controls aren't just training sessions, they're observable actions. This includes everything from maintaining a critical user register to a formalized leak/trap workflow. If you can't see the control in action, it doesn't exist. Data is only useful if it changes a decision. We don't need more data. We need the right data. Connecting production states to utility performance and linking specific defects to repair work orders and verified benefits. We should use measures that trigger action. Pair your lagging business outcomes, like specific consumption, with leading indicators like defect closure time or remote pressure loss. These leading indicators tell you if your system is actually being managed. Culture becomes durable through cadence. This means a quick frontline review every shift, a weekly check on control health, and an annual strategy reset. It escalates exceptions without turning every single issue into a time-consuming meeting. Technology should reinforce your discipline, not replace it. Use submetering and analytics to find the where and why of loss. Tools like ultrasound for leaks or CMMS integration for repairs are force multipliers for a disciplined team. Finally, we must apply, verify, and then sustain. Start small, prove it works with hard evidence, and then scale across the entire site. Let's look at a case study. Many teams see 4 compressors running and think they need a 5th. They see high base load and high pressure drops, but they haven't diagnosed the system. The decision point is, do you buy more capacity, or do you fix the system you already own? The intervention isn't just a repair, it's a framework application. Mapping consumers, baselining low load, and diagnosing the pressure zones. We find that the need for more air was actually a symptom of poor distribution and excessive leaks. The results of a successful intervention are clear. Base load falls. Remote pressure is met at a lower set point. And suddenly that essential 4th compressor can stay off. We deferred capital spending by measuring the system first. I want you to try this tabletop exercise later. If operations wants to raise boiler pressure because of a complaint, how would you apply the flow 6 model? What would you measure first? This is how you practice making evidence-based decisions. Beware of common traps. Running an energy project outside of maintenance is a recipe for failure. Similarly, tagging leaks without actually scheduling the repairs is just paperwork. You must address the demand, the distribution, and the supply together. Here is your 90-day roadmap. Spend the first month seeing and baselining. The second month is for piloting and correcting defects. By the 3rd month, you should be verifying benefits and locking in the new ownership cadence. When communicating with management, speak the language of value. Don't just talk about kilowatt hours, talk about release capacity, deferred capital, and avoided production risks. A credible business case includes both the costs of repair and the value of avoided failures. To maintain high standards, use this 12-point field audit. Only score what you can actually observe or trace. This keeps the focus on the reality of the plant floor rather than what is written in a binder in an office. As you head back to your plants, remember, the utility bill is actually a reliability report written in flow and pressure. Commit to no raised set points without diagnosis, no tag losses without work, and no savings without service verification. For those who want to go deeper, I provided several resources from the DOE and other experts. These handbooks and videos are excellent for technical deep dives into compressed air and steam systems. I also want to acknowledge the sources for the industrial photography used throughout this presentation, which help bring these invisible systems to life. I'll leave you with one question. What is your plant consuming while producing nothing? Find the answer to that, and you'll find the path to a more reliable, profitable operation. Thank you.